In this lecture, we are going to talk about the Clebsch-Gordon coefficients, what they are, how to calculate them, and so on. But before we get there, let me just remind you of what the context is. We are talking of a composite system made up of two subsystems, and these two subsystems have angular momentum J1 and J2. What that means is that every state of the subsystem A that we are considering is a J1 square eigenstate with eigenvalue small j1 into small j1 plus 1 h cross square, and a similar statement can be made about every state of system 2 or system B. Of course, that doesn't mean that each of these subsystems have only one state. For this given value of J1, for example, the Jz eigenvalue, J1z eigenvalue M1 can take two J1 plus 1 values, namely from minus J1 plus 1 all the way up to plus J1, and a similar statement can be made about the subsystem B. It has two J2 plus 1 independent states. Now the composite system has a basis which is 2J1 plus 1 into 2J2 plus 1, which has 2J1 plus 1 into 2J2 plus 1 elements. So that's the dimensionality of the composite space that we are dealing with here. Well, if we want to talk about rotation of the states in this composite system, what we should use is a total angular momentum operator J for the whole composite system. And let me just remind you that J is J1 direct product with I2 plus I1 direct product with J2. We covered all this in the last lecture. And a very obvious and simple choice of basis that we have for the states is simply take all the J1 M1 states for fixed J1, but you do have two J1 plus 1 such states, and take all the J2 M2 states, 2J2 plus 1 of them, form the direct product, and the set of 2J1 plus 1 times 2J2 plus 2 states give you a basis for the composite system. And the nice thing about this basis is that the vectors which make them up are eigenvectors of four commuting operators J1 square, J1z, J2 square and J2z, and so it's easy to tell how these states are going to evolve when you rotate the coordinate system, at least for individual systems. And it's easy to calculate various results which involve angular momentum operators. However, for the composite system, rotation is really carried out by the total angular momentum operator, as we have said, not the individual angular momentum operators of the individual subsystems. So it would have been nicer if we could have states which behave nicely under the action of the total angular momentum operators. So what we are looking for are eigenstates of J square, Jz. Of course, there will be a lot of degeneracy even after that. To lift that degeneracy, we need further labels, and for that we seek other operators which commute with J square and Jz. Again, we dealt with all this in the last lecture. So we need eigenstates of J square, Jz, J1 square and J2 square. These are the two operators, or these four operators commute with each other. And on the screen right now you can see that we have used a slightly unusual notation which does happen to be pretty standard in some books. Instead of using the angular bracket for kets, I have used a rounded bracket. Just to remind you, we are going to use angular brackets for subsystem 1 and subsystem 2 kets or direct product of those kets. So when I write J1, J2, semicolon, M1, M2 inside an angular bracket, it will mean that the state we are talking about is an eigenstate of J1 square, J2 square, J1z, J2z. Whereas here we are using rounded brackets, and this is just being done to distinguish them from the other states. So J1, J2, semicolon, Jm in a rounded bracket or half rounded bracket, of course, there's a bar on one side, These are eigenstates of j square, jz, j1 square and j2 square with the obvious eigenvalues. Now, where is the Clebsch-Gordon coefficient in all of this? Notice that the states j1, j2, semicolon, m1, m2, direct products of j1, m1 and j2, m2 kets do form a complete basis for our system, composite system. Since j1, j2, jm are actually states in this space, you should be able to expand these states in terms of those states. Actually, it goes a bit further than that. J1, J2, Jm, if you take all possible j's and m's for this particular situation, do form a basis of the state as well. So basically, when we are going over from J1, J2, M1, M2, that is direct product of J1, M1 and J2, M2, to these states J1, J2, Jm, we are actually carrying out a change of basis. But the important thing is, these vectors J1, J2, Jm here can be expanded in terms of J1, J2, M1, M2 with coefficients in front. And those coefficients are exactly what we call the Clebsch-Gordon coefficients. So let's get into that. But before that, let me remind you that even if we did not know that J1, J2, M1, M2 for fixed J1, J2 form a basis of the Hilbert space that we are talking about, if we took all possible J1, J2, M1, M2, that is all J1 prime, J2 prime, M1 prime, M2 prime values allowed, they would definitely form a complete basis, an infinite dimensional complete basis now, because J1 prime and J2 prime can take arbitrarily many values. These infinite dimensional, this infinite element basis would definitely be a basis for the complete Hilbert space of all possible states of the system, not just spin J1, spin J2. So J1, J2, Jm can obviously be expanded in terms of them. So we should be able to write this. And notice this part in purple out here is nothing but a resolution of the identity. J1 prime, J2 prime, M1 prime, M2 prime, if you take all possible J1 prime values, all possible J2 prime values, and all possible M1 prime and M2 prime values corresponding to the J1 prime, J2 prime values, this particular thing forms an identity. So all you are saying is you are applying the identity operator on J1, J2, Jm. And this of course is correct. However, it is easy to see that we don't really need to deal with this huge sum over J1 prime, J2 prime, M1 prime, M2 prime actually, because many of these coefficients, which are really inner products between this or this bra acting on this cat, will be 0. And why? Well, notice that these cats are eigenstates of J square, Jz, J1 square, J2 square, whereas these cats here are eigenstates of J1 square, J2 square, J1z, J2z. So both of them are actually eigenstates of J1 square and J2 square. So if J1 and J1 prime are different, then the corresponding cats are eigencats corresponding to different eigenvalues of the operator J1 square. Similarly, if J2 and J2 prime are different, they are eigenkets of different corresponding to different eigenvalues of J2 square. Now there is one very important result which you all know, that eigenkets belonging to different eigenvalues of a Hermitian operator are mutually orthogonal. So J1 prime and J1 have to be the same for this matrix element to not vanish. Similarly, J2 prime and J2 would have to be the same, otherwise the matrix element here, this overlapping term, actually not the matrix element, would actually, it is the matrix element of the identity, but that's just a trivial thing. This overlap term here would vanish unless J1 equals J1 prime and J2 equals J2 prime. Hence, this horrible looking sum simplifies a bit there is no sum over J1 prime and J2 prime. They have to be equal to J1 and J2. So what we have ultimately is this. J1, J2, Jm can be expanded in terms of J1, J2, M1, M2 with these terms here as coefficients. Of course, we already knew this because remember, we have been saying over and over again that if you take all the states J1, J2, M1, M2 with M1 and M2 running from minus J1 to plus J1 and minus J2 to plus J2 respectively, they form a complete basis for the system that we are talking about, where the first system is in angular momentum J1 and the second system has angular momentum J2. So it's not a surprise that we can expand this state in terms of just these basis vectors. And in other words, we could also say that this sum here of this Clebsch, which is an operator and summed over all possible M1, M2 values, is really the identity operator for the subspace that we are talking about, the spaces of the composite system, where spin A or system A is definitely having angular momentum J1 and subsystem B definitely has angular momentum J2. Now of course what we have here is an expansion of a ket in terms of a basis vector, and here we have the coefficients. These coefficients are what are called the Clebsch-Gordon coefficients. So these are the things that we are going to talk about. The coefficients in the expansion of J1, J2, Jm in terms of J1, J2, M1, M2. As we have already said, this is really a change of basis. So if you take all these coefficients together, put them in a matrix, that gives you the transformation matrix from going from one basis to another. Now this notation is a bit too cumbersome. You have to write a lot here. But since we are dealing with situation where system A always has angular momentum J1 and system B always has angular momentum J2, and we are just looking at those states, the J1, J2 labels are going to be the same on both sides of this notation. So what we will do is we are going to drop them and adopt a simpler notation, M1, M2, Jm. You must remember that all of these are just shorthand, so each of these kets here or the bras here which make up this overlap actually have the J1, J2 in front of them. So it's J1, J2 semicolon Jm and J1, J2 semicolon M1, M2. We just don't write the J1, J2 semicolon part in both of them. This is just to cut down on the notation a bit, make it look less intimidating that it has to be. But sometimes we have to pay a price, that is, we have to keep on remembering that J1, J2 labels are still really there, and in some calculations that may be important. So sometimes what I'm going to do is we are going to go back and revert to this big notation when I want to make points clear. But once you get the hang of it, I'm pretty sure you will be able to sort of work in your mind that there is a pair of extra labels in each one of these notations. So one very important theorem that we have about the Clebsch-Gordon coefficients is M1, M2, Jm, this Clebsch-Gordon coefficient, must vanish unless something very simple happens. Unless the M label here, which remember is the eigen value of Jz, and these M1, M2 labels here, which are respectively eigenvalues up to a factor of h cross, of course, of J1z and J2z, obey a rather obvious relationship. M is M1 plus M2. Now why does that come about? Simple. We know that Jz is J1z plus J2z. Let me warn you, this really is a highly shortened notation. This really should have read Jz is J1z direct product with identity 2 plus identity 1 direct product with J2z, which promotes of course J1z and J2z to operators, to being operators on the composite space, on the same composite space, so that they can be added together. But you have already seen how to work with this, and I'm pretty sure there will be no problem with this shortened notation. Now what we know is Jz minus J1z minus J2z, this thing, this operator is 0. So if you sandwich that between the bra M1, M2, J1, J2, M1, M2 and the ket Jm, J1, J2, Jm, you must get 0. After all, the matrix elements of a null operator has to be 0. But what is Jz acting on Jm? It's actually mh bar acting times Jm. So if you look at just the first piece, the piece involving Jz, this simply becomes mh bar times m1, m2, Jm. And similarly, J1z acting on m1 gives you m1 h bar, J2z acting on m2 gives you m2 h bar. So this whole expression simply means that m minus m1 minus m2 times h bar times this overlapping term, the Clebsch-Gordon coefficient, has to be 0. And what this clearly says is that unless m equals m1 plus m2, the Clebsch-Gordon coefficient here must vanish. So that's one very important property. The next very important property of the Clebsch-Gordon coefficients is called the triangle inequality. And the name should be obvious the moment you take a look at it. It says that the Clebsch-Gordon coefficients vanish unless the value of j in this m1, m2, jm is bounded between an upper limit of j1 plus j2 and a lower limit of j1 difference j2. This of course is exactly what we would expect if j, or rather jh cross, where the length of a vector which is the sum of two vectors j1 and j2 with individual lengths j1 h cross and j2 h cross. Remember, j is j1 plus j2, so according to elementary vector algebra, j1, j2 and j are supposed to form a triangle, and this triangle inequality sort of bears out that statement. I must warn you, however, that this thing has to be taken with a pinch of salt. After all, the length of the j vector is not really j1 h bar or j h bar. The closest that you can really come to the length is root over j into j plus 1 h bar and so on. However, this picture of j vector being a vector with side j h bar etc. actually works rather well to sort of understand some of the results that come out of quantum mechanical calculations. And this picture actually forms the basis of a model, a semi-classical model involving angular momenta, which you must have studied in the last semester, the so-called vector atom model. The vector atom model really is a way of writing down quantum mechanical calculations without using quantum mechanics proper, just by treating the angular momenta involved as ordinary vectors. Of course, you must make some compensation for the fact that there is really quantum mechanics behind the scenes. So you would have to live with the fact that despite the triangle inequality, the length of the vectors are really not j, j1, j2, h bar respectively. They are root over j into j plus 1, root over j1 plus 1, j1 into j1 plus 1, root over j2 into j2 plus 1 and so on. So these well, the vector atom model is actually a very successful way of dealing with many of the calculations that we are talking about here. But what we are going to talk about in these lectures actually provide the proper quantum mechanical basis for those calculations. So in the next part of this lecture, we are going to look at exactly how to calculate the Clebsch-Gordon coefficients.